In this lesson, we'll learn about transition metal reactions. In the last video about transition metals, we left off at the effects on the color of transition metal compounds due to the oxidation number and coordination number. Now we'll learn about the reactions of transition metals. So at first we begin with the reaction of transition metals and hydroxides. So the hydroxide we usually use are sodium hydroxide and potassium hydroxide. Now we'll learn about the reactions for hydroxides in excess and in small quantities. So we start from chromium. So for chromium 3, the complex for chromium 3 is CrH2O6 3+. This is in aqueous form, and if I add a few drops of OH minus to it, this will form a green precipitate of CrOH3 H2O3, and the charge will be 0. So the number of hydroxides that are joining over here is equal to the charge over here for the cation. This will also give us 3H2O. This will be a solid, and we need to remember the colors over here. So for chromium, this is green, and to balance the equation, I'll have 3OH minus. However, if this is when we have only a few drops of OH minus. If I have excess OH minus, this will react with further OH minus. So if I want to write the overall equation, this will be CrH2O6 3+ plus OH minus. Now this 3 water will also be replaced with OH. Will be left with CrOH6. The charge over here will be 3 minus, and we'll have 6 water. This is aqueous. For this we'll need 6 OH minus. So this is when we have a few drops of OH minus, and this is in excess. And the color of the solution is also green. This is a green solution. The one on top is a green precipitate. Now up next we'll learn about manganese 2, which is Mn2+. Manganese 2 reacts similarly when we have OH minus reacting with it. When OH minus reacts with manganese 2, we'll get MnOH2 H2O4. We have a charge of 0. This is a solid, and we get 2 moles of H2O. So we have 2 OH minus. In this case, it doesn't matter if I have excess or a few drops. It will always show this reaction. And the color of this compound is off-white. So the precipitate is off-white in color, and there's an interesting property about it that we might have to remember, and that is that it darkens. If it's kept standing over there in air, it will turn gray. So it darkens gradually if we keep it in open air. The next one will be iron 2. We'll learn about 2 ions of iron. One is iron 2, the other is iron 3. In case of iron 2, we have iron H2O6 2+. This will react with OH minus, giving us FeOH2, H2O4. The charge is 0. This is a solid. We get 2 moles of water out from here. We have 2 moles of OH minus. This is also the same case. So it's the case if we have excess or few drops. The color of this precipitate is mud green. Now up next we learn about iron 3, Fe3 plus. Its complex is FeH2O6 3 plus. This reacts with OH minus to give us FeOH3 H2O3 solid and 3 moles of water. We have 3 moles of OH minus here. The color of this precipitate over here is red. The same is the case for Fe3 plus, where we can have few drops or excess OH minus, but it will show the same product. It will not dissolve again. For chromium, it forms a precipitate and then dissolves. For the other cases, it doesn't dissolve, the precipitate remains. Now we learn about cobalt 2, which is CO2 plus. If you don't write your O properly, cobalt might be misinterpreted as carbon monoxide, so you need to be a little careful when you write the form of cobalt. We have COH2O6 2 plus plus OH minus. This will give us COOH2 H2O4. The common, this is a solid, and we have 2 moles of water and 2 OH minus over here. The color of this thing over here is blue, so we get a blue precipitate. However, there is an interesting feature for cobalt as well. It is that this over here turns pink on standing, and we don't have any definition for it whatsoever. We don't have any explanation for it yet. The color change is also a feature for Fe2 plus, so this will turn brown at the surface because this over here is oxidized into this product. So this turns brown on standing. Now for the next one, we'll learn about nickel 2. We have nickel H2O6, a charge of 2 plus plus OH minus, giving us NiOH2 H2O4 solid plus 2 water, and we have 2 OH minus over here. For the previous case as well, we have the same scenario if we add excess or a few drops. Same over here for nickel. The color of NiOH2 H2O4 is green. This is a green precipitate over here. Then we go to copper 2, CO2 plus. We have CuH2O6 2 plus plus OH minus, which gives us CuOH OH2 H2O4 solid plus 2 moles of water. So this is 2OH minus over here. The color of this precipitate over here will be blue. So this is a blue precipitate. This is also the same case for few drops or excess. Finally, we go to zinc. We have zinc 2 Zn2 plus. We have ZnH2O6 2 plus aqueous plus OH minus, giving us ZnOH2 H2O4 solid plus 2 moles of water, 2H2O liquid. So we have 2 OH minus here. For zinc, the case for a few drops and excess is different. We'll have dissolving over here. This precipitate is white in color. We have a white precipitate. Now zinc reacts with excess OH minus. So ZnH2O6 2 plus reacts with excess OH minus, so 4 OH minus over here, and forms ZnOH4 H2O2. This is different from what chromium does. Chromium forms CrOH6 3 minus. You have to remember the fact over here. This has a charge of -2. This will be aqueous, and we get 4 moles of water being produced. This is for excess OH minus. The solution is colorless over here, which is obvious because zinc is not actually a transition metal, it's just a D block element, but not a transition metal. These reactions are called deprotonation. These are not substitutions basically. The thing that happens over here is not a substitution. We don't have OH minus replacing the H2O inside the complex. We basically have this OH minus causing the water in the complex to lose its hydrogen. So the hydrogen over here is taken away by the OH minus, so the OH minus becomes water and this becomes OH minus, since the H plus ion goes from here to here. So it's called a deprotonation since we are removing protons. H plus ion is a proton. We are removing protons from the complex, so the type of reaction is called deprotonation. Next up, we'll learn about the reactions of metal cation, transition metal cations with ammonia. It's pretty much the same. The only cases that it's different in are the cases for chromium. It's also different for nickel, copper, and zinc. So these are the cases where it's different for NH3. In the other cases, we can just replace the OH minus with NH3. The products will pretty much be the same, just in place of water we'll have NH4 plus. So if I write down all the reactions, we start from chromium. For chromium we have an exception, so we'll discuss that. So Cr3 plus, so the complex is CrH2O6 3 plus, and now we are reacting with ammonia. If there is few drops of ammonia, the reaction will be the same. So we'll get CrOH 3H2O3 plus we have 3NH. So we have 3NH3 over here, not 4. And on the right we'll have 3NH4 plus. And in case of excess ammonia reacting, we have this plus 9 moles of ammonia. This will form CrNH36 3 minus 3 plus. This is 3 plus, and we'll have 3OH minus. It's better to not go directly from here. We'll take this as the thing we're reacting with. Basically, when we write down a reaction from this to this with excess ammonia, we are showing the first reaction and then showing the second reaction, because the excess ammonia will react with this product over here. So if I show that, we have CrOH3 H2O3 solid plus ammonia. This will form CrNH36. The charge of the chromium central ion is 3 plus. The charge of each ammonia is 0. So this is a charge of 3 plus. Then we'll have 3OH minus over here plus 3H2O leaving from here. The first reaction is a deprotonation. We are removing protons from the H2O of the chromium complex. The second reaction, however, is a substitution. We are replacing the OH3 and H2O3 with ammonia. We'll have 6 moles of ammonia here. This is a substitution reaction. The color of this is already green, we know that. This is a green precipitate. This over here will be a green solution. So these are the ones that will be the same. We just have a change in this product over here. For OH minus reacting with the transition metal, we had H2O forming here. Instead of H2O, we'll just have NH4 forming here. The rest of the product are the same and their colors are also the same. So this is mud green and this is red brown. Now here the exceptions start beginning with cobalt. For cobalt CO2 plus, we had COH2O6 2 plus reacting with ammonia. This will form a COOH 2H2O4. So this one is common over here. This is also the case for OH minus as well. But this is only for a few drops. In the other cases where I just showed one example, this is for both cases of excess and a few drops. This is few drops. This is excess. For cobalt as well, we'll have a different reaction when it's in excess. So we have COOH 2 H2O4 solid with a charge of 0 reacting with 6 moles of ammonia. This will form CONH3 2 plus and forms 2OH minus and 4H2O. This over here is this is a deprotonation over here. The reaction on the top and the reaction on the bottom is a substitution. The color of this over here We already know the color of this. This is blue and it turns pink. The color of CONH36 is brown. Next up, we have nickel 2 plus, so NiH2O6 2 plus reacting with ammonia. When it's a few drops, we have two ammonias forming NiOH2 H2O4, the common thing, the same as OH minus, just the NH4 being here. This is for a few drops. In case of excess ammonia, we'll have NiOH2 H2O4 reacting with 6 ammonia. This will form a similar product. We'll have NiNH36. This will have a power charge of 2 plus, and we'll have 2OH minus plus 4H2O. Next up, we'll have copper. This is for excess. Next up, we have copper 2, so copper H2O6 to the charge of plus 2. When we have a limited ammonia, this will react to form CuOH2H2O4. The fact that this is a deprotonation reaction is more evident here, since we are not putting in NH3 over here directly. And this solid over here forms along with 2 moles of ammonium ions. This is the case when we have a few drops of NH3. If we have excess NH3 with copper, we'll have CuOH2H2O4 reacting with 4 moles of ammonia here, not like the previous two, and this will form CuNH34H2O2. This is a bit different from the previous two. We have to remember this. This has a charge of plus 2, and alongside it we'll have 2 moles of OH minus and 2 moles of water. Now finally for zinc, we have to know the colors of this. This thing over here is a blue solution. We already know the color of this compound, so we'll not dive into that. This compound we know the color of. We also know the color of this compound. We don't know the color of this. This will be deep blue in color. We can also call these substitutions as ligand exchange in a better way, because in this case we are changing ligands. This substitution is causing a change in ligands. Beforehand we had OH and H2O ligands, now we have NH3 ligands. So we can call this ligand exchange. That's a better term over here. Now finally we have the reaction for zinc. Zinc is pretty much the same. This case is the same for a few drops, just the ammonium different. This case, when we have excess ammonia, we'll have a case like copper, not like the other ones. A case like copper will have 4NH3 reacting to give us Zn NH34 H2O2. This has a charge of 2 plus. We have 2 OH minus being formed and 2 H2O being formed. This is colorless again. The fact this is colorless because zinc is actually not a transition metal. Now we can learn about some of the exceptions that we have learned in this case. Not exceptions, just additional forms. So over here we have one that it turns pink on standing. We don't yet have an explanation on this, so we'll not be asked questions for that. However, we might be asked questions on why this turns into the mud green precipitate turns into red brown. We might have to explain why. This is because when the iron 2 hydroxide stays in air, it gets oxidized by the air and forms iron 3 hydroxide. And in the case of manganese, this off-white substance darkens because the MnOH2 is oxidized into MnO2, which is brown in color. You'll have to remember this. So if I want to show the mechanism of something, a deprotonation for example, I'll show an example with copper. So we have CuH2O6. This has a charge of 2 plus. And an OH minus will attack this. In fact, deprotonation might be caused by a water outside as well, but we'll not show that right now. We'll show an OH minus outside. I'll show one of these bonds properly. Now we know that this hydrogen will be electropositive due to the fact that the oxygen is electronegative. Now the lone pair of OH minus will attack this electron deficient area around hydrogen. This will cause the OH bond to break heterolytically with the electrons going to oxygen. So this goes into being CuH2O5. The other ones are unchanged. And in this case, we have an O minus and an H. So we have an OH minus here. And we have another H2O here. And outside this, we'll have an H2O being formed. This charge will reduce from +2 to +1. Since we have a negative over here, we have a +2 here and a minus over here. +2 minus 1 is +1, so the overall charge is +1. This is the example of a deprotonation reaction. So this is a deprotonation. This could have also worked with water instead of OH minus. Just in place of H2O, we would have H3O plus in that case. So the white is in if we did the thing with OH minus. The blue one is if we did it with water directly. And that's it for the common reactions of transition metals. In the next video, we'll learn about the use of transition metals as catalysts. And after that, we'll dive deep into each transition metal that we have to learn about, especially chromium and vanadium. That's it for today.